Today in class, we started talking about sound in specific, which is a longitudinal wave, unlike the transverse waves that we were talking more about last time. So, when I say a longitudinal wave, that means I'm talking about the compression of particles, and so that the motion of the medium is actually in the same direction as the motion of the wave. Unlike with a transverse wave, where the motion of the wave is perpendicular to the the motion of the wave is perpendicular to the motion of the medium. Okay, so if, say for example, like I had in class, I had a tuning fork, then what happens with the tuning fork is that you have air molecules that are around. You strike the tuning fork starts vibrating, and what happens is that on the outswing, it will actually push against the air molecules that are next to it. And so what that does is that it bunches up the air molecules, pushing them together. And you have the other air molecules out here, and now you give an energy to these air molecules. They're going to keep going in that same direction. Okay? But now these are clumped, and they're going to keep going in that direction. They're going to keep on impacting the other air molecules that they meet along the way. So that it's going to keep on going out, in, out, in, out, in, and when it goes in, you're going to have air molecules that have to rush in to fill the space, but it's going to be a much less dense area than what would actually be here where it was compressed. So what you have after a number of iterations is a region of compression, a region of rarefaction, which is where it is not so dense, and regions of compression, regions where it is not so dense, etc., etc., depending on the specific vibrational frequency of the tuning fork. Okay, so it makes this compression that then propagates out through the rest of the medium. So that would be the longitudinal wave. We can represent this as a transverse wave if we think about it this way, that the peak of this transverse wave would be the place where it is the densest. The place where it is the least dense would be the trough of the wave. And then back up to the peak, and where it's most dense, the trough where it's least dense, etc. So we can still think about it in terms of sines and cosines for simple harmonic motion with regard to the waves, if we think about it in this representational form, where this is actually a map of the density. So the density is the biggest here, the density is the smallest here, you have the equilibrium density in the middle. Okay. The speed of the sound in whatever medium you're talking about is set by two things. That is the bulk modulus of elasticity of the fluid and the actual density of the fluid. So you have some, just like with the speed of a wave on a string we talked about, where that was equal to the square root of the tension force divided by the linear mass density, we have something that is some property of the medium itself that says how easy is it to move, how elastic is it, how much can it stretch. The more something is pulled taut, the less it has freedom to move, divided by some density. So this is just the linear mass density, this is the actual volume density. Okay, so it's some elastic property divided by the inertial property with regard to how much mass you have in any given volume. Okay, so the sound, the speed of sound actually also depends on temperature. And so, at least, and if we want to modify that for air in specific, using the bulk modulus of air, density of air, all that stuff taking into account the temperature at that point, you end up with 331 meters per second times the square root of the temperature divided by 273 Kelvin. Okay, so that if you're at room temperature, around 293 Kelvin, room temperature goes from like 293 Kelvin up to like 298 to 300 Kelvin. If you're at 2 193 Kelvin, then the speed of sound in air is 343 meters per second. Okay. So basically, that's how fast, assuming that this room is at 293 Kelvin, that's how fast my words are going to the microphone on the camera right there. Okay, they are moving at 343 meters per second because that's how long it takes, well, the distance it covers and the time it takes to actually have that happen because of the properties of the air, the medium that the sound is actually traveling through. It depends on the medium because it is only propagated by the fact there is a medium there. If we want to talk about the loudness or softness of sound, that gets at the intensity of the sound. So the intensity, the volume level of the sound, is equal to 1 over the area times the change in energy over the change in time. What does this mean? This means that it is the energy flow, the rate of energy flow, past a surface of area A. Okay? So if I'm talking about this palm here, okay, and I have sound waves as I'm talking to my palm here that are impacting this palm, and you know, if it were transparent to sound, they could go straight through it, right? So we're talking about the rate of energy flow as it passes through this surface area A. Okay? If we're talking about something like, well, like sound, like this, okay, then we can also represent this energy per time as the power of whatever the source of the sound is. Okay? Because power is watts, which is joules per second, which is exactly what the rate of energy flow is. So this also equals the power over the area. So if we have something that's emitting sound in a spherical way, like say we have, I mentioned this in class, we have a tuning fork that is sending sounds in all directions. Okay, the sound starts here and then keeps on propagating out through the air in spherical shells, taking up more and more space. So you have the power that gets diluted over that actual space. It keeps on going down by the surface area. The surface area of the sphere is 4 pi r squared, so the intensity for an object that's emitting sound spherically is the power divided by 4 pi r squared, where r is the distance from the source. So someone who is sitting right here next to the tuning fork is going to hear it much more loudly than someone who is sitting way over here. Okay? And it will drop off by this factor of r squared in the denominator there. Okay. So, the human ear is limited in how it can pick out differences in intensity level, and so because of that, we actually have developed a system of an order of magnitude way of looking at the intensity level, which we call the decibel system. Okay? And the reason why is because of the gigantic range of intensities. So, at 1,000 hertz, okay, at a frequency of 1,000 hertz, the faintest sound that you can hear has an intensity of 1 times 10 to the minus 12th watts per meter squared. That's called the threshold of hearing, because that's the faintest sound that you can hear at this standardized value. Now, if we keep increasing the intensity, you can keep tolerating that until it starts causing you pain. And the threshold of pain is just 1 watt per meter squared. So there are 12 orders of magnitude from the faintest sound you can hear at this frequency to the threshold of pain. And so because there's that much of a range, you want to actually deal with this in terms of orders of magnitude or powers of 10. And so we use the decibel system, where the decibel level is equal to 10 times the logarithm of whatever intensity you're talking about divided by the threshold of hearing. Okay, so I0 is going to be 1 times 10 to the minus 12 watts per meter squared. Okay. If you are at the threshold of hearing, that's 1 times 10 to the minus 12 divided by 1 times 10 to the minus 12, which is 1. The log of 1 is 0. And so the beta, standing here for decibels, will end up giving you 0 decibels. So the base decibel level would be 0. Okay. If we go all the way up to the threshold of pain, then that means that this is 1 watt per meter squared divided by 1 times 10 to the minus 12th, which ends up giving you 10 to the 12 inside here. And the log of 10 to the 12 is 12, and so the decibel level for the threshold of pain then is 120 decibels, because you multiply by this factor of 10 out here. Okay. So really, the tolerable region, the tolerable range for hearing goes from 0 decibels to 120 decibels. Okay. And we have to be able to deal with how the intensity changes relative to the threshold of hearing to be able to talk about the decibel system.